Hello everyone. So in the previous lecture we saw the idea of overfitting and also some classification metrics that you can use to assess your model and certain validation strategies such as the train test split or the cross validation method. In this lecture we are going to look at the concept of decision boundaries. What do they mean and how they tie up to this overfitting setup and see it will help you inculcate more the idea of what overfitting is, and also it generally serves as a nice visual representation of what your model is actually performing. So we'll start off with decision boundaries. Now so far we've covered three models in the course, in this three supervised learning classification models in the course. So the first one was KNN, the second one was decision trees, and the third one is neural networks. We will look at all the three models decision boundaries in this particular lecture. So firstly we'll start off with KNN. More specifically we will discuss the 1NN model. So KNN meant taking opinions from the k nearest neighbors in your data set. The distance could be Euclidean distance, or as we covered in the live session, the cosine distance and so on. So but we get a set of neighbors, and the top k neighbors we ask them to vote on their decision, and then we consider that. In the 1NN model we are only looking at the closest neighbor, so which is 1. So just one, the closest neighbor, we'll see what they are voting for, or in other words what the label is or the y value is for them in our data set, and classify the same thing for our for the point that you're trying to predict now. So we'll have a look at how the decision boundary looks like. So suppose we'll have two classes. So suppose this green class will be my positive class, and then I'll also have a red class which is my negative class. These classes could indicate anything. For example, we saw previously the bank example where there was Hari, Susan, John, Smith, with the classes being yes or no to being sanctioned for a loan. So we will consider that example itself. So let me plot some points. So have these points. Suppose the data set had, sorry, I should use the colors. So for example, this is my data set. Okay, and maybe we'll put in some outliers also over here. Yeah, so this is my data set. Now this is what the addition boundary is, right? So I'll come to that. Now first of all, what is a model doing? A model takes as input some entity, an object, or so in the bank case we considered every person to be just an age and a salary pair, right? So in other words, they are just some particular point on this particular graph, and then using that the model took those coordinates as input and later threw out an output as its prediction. So and now since we are talking about a 1NN model, we want to see in this particular graph all the possible points here, and then just kind of color them, saying okay, if my point is in this particular region I am predicting no or negative, or if it is not, if it is in some other region that is colored green maybe, then that would be my positive class. So this is what we have. So what our model is essentially doing is, so if since we in generally in the binary classification setup, our model takes in some x and then throws out it in most cases it actually gives a probability, like we saw in the neural network case where you got our outputs to be 0.9 and 0.1, where I think 0.9 would be given as the probability or the confidence a model has in its particular representation. So that so this model, so we have it outputting some number between 0 and 1, where this is the probability of, say, it being in the positive class, probability of positive class. The more higher the probability, the more confident the model is on its particular prediction. And so whereas this point, this x actually is at least here in a two-dimensional space, since we only covered age and salary, but in a general case this will actually be in a n-dimensional space. So Rn is just the space of all vectors or a collection of n numbers in the n-dimensional space. So we have this, and now what we will do is, this is my data set. I will fit my model in this. The model, now to find the decision boundary, I will apply this model across my entire space and see at which places my model will predict positive, which places it will predict negative, and color it accordingly. We'll loosely call it coloring, but we look at that now. So now before I start filling in my boundaries, to recap, in KNN we talked about the closest neighbor setup. Now suppose say I have these two neighbors, so these are in my data set. Okay, I'll color these as well. So I have a green point here and a red point here, let's say, and now suppose my point was here, right? Now which one would be the closest neighbor for this gray point? Would it be the green point or would it be the red point? This is not worth pausing for, but I am sure you guys would have said it's the green point, because the distance between this is greater than the distance between these. Yeah, because if you consider Euclidean distance, you will have that this point is closer. Whereas say suppose I consider, so okay, our prediction is green. Okay, now perhaps there's another point over here, then clearly this particular point will actually be predicted with red, right? Now what we'll do is, we are doing this for the entire region over here, and then when we do that, we can kind of see a boundary where this is in the extremal case, where crossing the boundary on one side will give a green prediction and crossing the boundary on the other side would give us a red prediction. So if I am to do that, so if I am to do that, this perhaps you must pause and think on where the decision boundary is. It's quite evident, and the answer would be this one, something like that. If you notice, this is actually just the perpendicular bisector of the line connecting these points. Yeah. So this is just a perpendicular bisector that of the line connecting my 2 points in the data set, and this is actually our decision boundary, right? Because in this particular setup, at least, what we'll do is, if we have a new test point that is incoming, my model will check if my test point is towards the right of the decision boundary. It's equivalent to just calculating the distance and checking, but another way of kind of describing what the model is doing, describing the behavior of the model, would be saying, if my points occur across the right of the decision boundary, then I will classify them as negative or red, right? So this is one side. The other side of the argument, if you will, would be, if it's coming on the other side of the decision boundary, it would just be the positive class. So all points over here will be classified to be positive, right? So now that we have this, we can go ahead and fill this diagram also. So first, what I'll do is, I will kind of find these bisectors for all these points, and then later I can color them accordingly. So I have these 2 points. So if I connect these, then I can see that points occurring here will be classified green, points occurring here will be classified red, and so for here also, right? So I have another kind of line here which will again classify. So I'll kind of have a diamond shape thing happening here. Similarly here, and yeah, a similar one here. These are all, I don't think you can, it's not that accurate. We'll soon have a look at it in orange. But yeah, this actually goes to the midpoint between these two lines. Then we also have this. So a bunch of diamonds, and if I am to color this, then you can see this would actually be red color. This would also be red. And then the rest would be green. Yeah, and you can keep coloring the space like this, and you can see why this works, right? So now we've not just done it for 1 point or 2 points, we've done it for all the set of points in the space, and we got this to be addition boundary. So later I can say if my test point is say appearing here, then it will be classified as a negative point. So this is what addition boundary is, and this is how addition boundary for a one nearest neighbor model looks like. I urge you to think about the cases where k is increased, so to 2, 3 and so on. It's a good thing to think about. We'll also now demonstrate this particular thing in orange, how you can